In this video, we introduce the T procedures used to test a hypothesis about the unknown mean mu of a population. Let's start with a reminder. Hypothesis tests contain a null hypothesis, a test statistic, and a test p-value. So how do we calculate the test statistic and p-value? When we want to test a null hypothesis about the unknown mean mu of a population, where the null hypothesis is that this parameter mu is equal to a specific value mu0, and we use a random sample of n observations from a normal population with a known standard deviation sigma, then we have a null sampling distribution that is normal, centered on mu0, with standard deviation sigma over square root of n. The test p-value will then be the area under that null sampling distribution for values of x bar that are at least as extreme in the direction of the alternative as the value calculated from our random sample. We can then standardize this sample mean x bar into a z-score, and our p-value will be the corresponding area under the standard normal curve for values of z as extreme as the one computed, or more extreme in the direction of the alternative. So for a one-sided alternative, the p-value will be the area in just one direction, the direction of the alternative. And for a two-sided alternative, the p-value will be the combined area on both tails. Now, this assumes that we know the value of the population standard deviation sigma, even though we do not know the value of the population mean mu. Now, this is a fairly rare situation. But what we've seen is that when the sampling distribution of x bar is normal, the standardized value z follows a standard normal distribution. But if we substitute the calculated sample standard deviation in place of the value for sigma, the population standard deviation, then the resulting test statistic t equal to x bar minus mu divided by s over square root of n follows the t distribution with degrees of freedom equal to n minus 1. This is very important because it means that we can still calculate a p-value even if we do not know the value of the population standard deviation sigma. Specifically, when the population standard deviation sigma is unknown, we can test a null hypothesis where our statement is that the mean mu of the population is equal to some value mu0, using the t distribution with degrees of freedom n minus 1 to calculate the p-value. The p-value in this case, when sigma is not known, will be the corresponding area under the t distribution with degrees of freedom n minus 1 for values of t at least as extreme as that computed in the direction of the alternative. Not knowing the value of the population standard deviation sigma is by far the most common situation, and the only one we'll be focusing on in this class. Now notice that the equations for the z and the t statistics were on a gray background. That indicates that you do not have to memorize those formulas or even to use them step by step, because we will instead be using technology for all the calculations needed to obtain the p-value of a test. For example, when we use a TI graphing calculator in class, and we want to test a hypothesis about the unknown mean mu of a population, we will go to the stat test menu and select the t-test function. This function can be used either with summary statistics or with raw data. Either way, it will require that we provide information about the null hypothesis and the direction of the alternative. Here's an example we've seen before. The individuals are healthy adults who switch from a traditional American diet to a vegetarian diet for 1 month. The variable is the change in cholesterol after switching diet, a quantitative variable. We have just one random sample of 20 individuals, and the parameter of interest is the population mean cholesterol change, which we shall call mu cholesterol change. Now, we want to know if there is evidence based on the study that in the corresponding population, there is a decrease in cholesterol on average. The population mean cholesterol change is negative. The null hypothesis and the alternative hypothesis will be statements about this parameter. The null hypothesis has a statement of no effect, says that there is no impact of switching diet. Some people's cholesterol might go up, some people's cholesterol might go down, but overall, on average, in the entire population of all healthy individuals who would switch diets like that, the mean cholesterol change mu is equal to 0. The alternative hypothesis is clearly one-sided because we would like to know if the switch in diet leads to a decrease in cholesterol on average. So our alternative is that mu cholesterol change is negative. If we use, for instance, a TI graphing calculator, we go to the submenu Stat Test, and then we select T-Test. We could have entered the raw data into a list and then select the data input. Instead, I will just use the summary statistics and therefore select the stats input option. Mu0 is what is the value of mu according to our null hypothesis. So in this case, it is 0. X bar was negative 19.75, S75. Sx is the sample standard deviation, 17.474. N is a sample size, 20. The alternative hypothesis is that mu is less than 0, so the second option. And that gives us the following output. First, we have our alternative hypothesis repeated to us, mu less than 0. Then we have a value t, that's our test statistic. It's negative 5.05. And then a value p, that's our p-value. It says 3.5 ... e negative 5. Remember that a p-value is a probability. It will always be a number between 0 and 1. But for very small p-values, whatever technology you use might round that number to a fixed number of decimal places, or it might use scientific notation, like here. So 3.5 e negative 5, that's roughly 4 e negative 5, which is 0.00004. Mathematically, that says that if the null hypothesis was true, we would expect results like the results of this study or something even more extreme to occur in about 4 in 100,000 different studies similar to this one. So something we would really not expect to see if the null hypothesis was true. Therefore, the study provides very strong evidence with a p-value of 0.00004 that on average, switching from an American diet to a vegetarian diet for 1 month lowers cholesterol in the population of healthy adults. There are many ways to write this as a sentence, as long as it is clear that the conclusion is about the mean mu of the population of interest. That means that we're talking about the change in cholesterol on average, or the mean change in cholesterol, and that's due to all healthy adults who switch diet, or the population of healthy adults after they switch diet. Now, another reminder, we've also talked about the assumptions behind parametric inference for a population mean. We have 2 conditions. The first one is that the data are a random sample from a much larger population. And the second one is fundamentally that we have a roughly normal sampling distribution for X bar. And this happens when the population is normal, or when we can rely on the central limit theorem to tell us that with a large enough sample size, the sampling distribution of X bar should be normal, even if the population is not normal. This is what we refer to as the robustness of the T procedures. The T procedures are robust to deviations from normality when the sample size is large enough because of the central limit theorem. For instance, we had seen that the distribution of cholesterol change values was roughly normal. We are also told that we have a random sample of healthy adults. Therefore, both conditions for the T procedures are met. When discussing T procedures for a confidence interval to estimate the unknown mean mu of a population, we also introduced the concept of match-paired T procedures. When we have pairs of data or repeated measurements on either the same individuals or clearly related individuals, we can compute a pairwise difference if we have a quantitative variable, and then that means that we have just one random sample of n data pairs. We will then use those calculated pairwise differences to calculate the summary statistics, the sample mean for the differences, x bar diff, the standard deviation for those n pairwise differences, s difference, and use those values for inference about the unknown mean mu difference of the target population. We can test the null hypothesis that the mean mu diff is equal to 0. There is no difference overall on average in the target population versus either a one-sided or two-sided alternative. Or we can obtain a confidence interval for the parameter mu diff. Mathematically, this is equivalent to a one-sample t procedure. Now, some statistical software offer as a convenience to either do a match pair t-test on the values before and after, in this case, or to do a one-sample t-test on the already calculated pairwise differences. We get exactly the same test statistic t and the same p-value because those are exactly the same procedure with just the extra step of having to calculate the pairwise differences.